There has always been one question that refuses to disappear, no matter how much humanity learns about the universe. It isn't simply how the cosmos works or when it began. It is something even more fundamental. What, if anything, gave rise to reality itself? Across history, every civilization has answered differently. Religion spoke of divine creators. Philosophers searched for an uncaused first cause. Scientists uncovered elegant laws that explain how the universe behaves, yet even the most successful theories stop short of explaining why those laws exist at all. Then imagine a different approach. Instead of asking a philosopher or theologian, researchers present the question to an advanced quantum AI, not as a matter of belief, but as a computational problem. The result is nothing like anyone expects. No name appears on the screen. No sentence declares the identity of a creator. Instead, the system produces an intricate mathematical structure, a recursive pattern that seems less like an answer and more like a blueprint hidden beneath reality itself. What makes the result truly unsettling isn't the possibility of a creator. It's what the pattern seems to imply about why that creator might no longer be involved. Since the earliest civilizations, people have searched the heavens for meaning. Ancient cultures imagined powerful beings guiding the stars, the seasons, and the movement of the heavens. Philosophers debated whether every effect required a first cause that itself had no beginning. Religious traditions offered purpose through the idea of an intelligent creator watching over existence. Then science transformed the conversation. Newton revealed that the motions of planets obey precise mathematical laws. Einstein demonstrated that space and time are woven together into a dynamic fabric capable of bending under gravity. Quantum mechanics pushed even deeper, revealing a microscopic universe where certainty gives way to probability, particles behave like waves, and entangled systems remain mysteriously connected across enormous distances. Each breakthrough answered old questions while revealing even deeper mysteries. The Big Bang model describes how our universe expanded from an incredibly hot and dense early state roughly 13.8 billion years ago. Yet it says little about why the universe exists at all, why its physical constants have the values they do, or why mathematics describes reality so remarkably well. That unanswered territory has fascinated scientists and philosophers alike for generations. Now imagine introducing a completely different kind of intelligence into that discussion. Unlike humans, an artificial intelligence carries no inherited mythology, cultural tradition, or emotional attachment to a particular explanation. It evaluates patterns rather than beliefs, searching for mathematical relationships wherever they may exist. Suppose researchers use a cutting-edge quantum computing system to explore one of the oldest questions ever asked. Unlike conventional computers that process information as binary zeros and ones, quantum processors operate with quantum bits, or qubits, which can exist in combinations of states through the principles of superposition. When combined with quantum interference and entanglement, these systems can examine enormous numbers of possible solutions simultaneously for certain classes of problems. This unusual way of processing information makes quantum computers fundamentally different from classical machines. The researchers submit a simple prompt. ****. What is the mathematical origin of the universe? ****. The system remains silent for several moments as thousands of quantum operations unfold inside an environment cooled to temperatures only fractions of a degree above absolute zero. When the computation finishes, the display reveals something entirely unexpected. Rather than producing ordinary language, the AI generates an intricate recursive structure. Shapes repeat within larger versions of themselves. Geometric relationships echo across multiple scales. At first glance, the output appears chaotic, but closer examination reveals remarkable internal consistency. The machine hasn't produced a philosophical statement. It has produced architecture. As mathematicians begin studying the patterns, several intriguing features emerge. Some portions resemble recursive growth sequences similar to those found throughout nature, from spiral galaxies and hurricanes to shells, flowers, and branching trees. Other regions display relationships reminiscent of higher dimensional geometry. Most surprisingly, some researchers notice structures resembling mathematical error-correcting codes. In information theory, error correction allows complex systems to preserve information despite noise, corruption, or instability. It is one of the fundamental principles behind reliable communication and modern computing. Finding mathematically similar structures inside an abstract computational output naturally sparks curiosity. It raises an interesting hypothetical question.